Okay, in this video we're going to do a couple more related rate examples. So, Mr. Danielson's walking north towards an intersection at a rate of 3 miles per hour. Ms. McKenzie is walking east away from the intersection at a rate of 2.5 miles per hour. At what rate is the distance between them changing? Mr. Danielson is 0.5 miles away from the intersection and Ms. McKenzie is 0.75 miles away from the intersection. So, let me draw this picture. Okay, put it right up here in the corner. We got a triangle. Okay, walking north, walking east. We're wondering about the distance. So if we name that X, maybe that Y. Okay. Now, the rates, let's put those over here. I know that dx dt, Miss McKenzie's rate, is 2.5. And I know that dy dt, the other rate, is -3. Now the reason it's negative is because the length of y, this length right here, as you're walking towards the intersection, the length of y is getting longer. The length x, however, is getting shorter. I'm saying this wrong. The length y is getting shorter, whereas the length x is getting longer. Okay, so that's why the rate for y needs to be negative, because this length is getting shorter. Of course, if we name this z, we're looking for dz dt. Okay, the equation is definitely going to be Pythagorean theorem. Derivative. And now we're going to substitute and solve. X, we're wondering what, so Miss McKenzie was 0.75 away, so her rate was 2.5. 0.5. And we're going to have to use our calculator and little Pythagorean theorem, knowing that this is 0.5, this is 0.75. We're going to have to use Pythagorean theorem and solve for the hypotenuse. And if you do that, that comes out to be 0.901. And so now we're solving for dz dt, so we would just divide by 2 times 0.901, like that. And that would solve for dz dt. And we could type that in our calculator, and we would get 0.416 miles per hour. Of course, the reason it's so small is because one length is getting shorter and the other is getting longer. They're not going away from each other. One's actually going towards the intersection. Okay, in this problem, this is a little bit different. We're going to look at an angle. Okay, so a man walks along a straight path at a speed of 4 feet per second. A searchlight is located on the ground 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating? Okay, so the picture here. We've got a searchlight. Okay, there's my searchlight. Beaming at this man walking along. Okay. So it forms a triangle, right? We could say X and Y. And we're looking for the rate that you have to turn the searchlight to keep up with the man. So we're looking for d theta dt in this case. Now, I've said before I don't like writing in changing quantities on my picture, but in fact, I have an unchanging quantity here. The searchlight is 20 feet away, period. Now, I don't have to put this in, but it will make the calculus a little bit easier later if I do. Okay. The one rate I know is how fast he's walking. That's dx dt. and I'm looking for the rate at which the angle is changing. That's d theta dt. Now, this is the first example I've done where we have an angle. So now we introduce the trig functions. Okay, it is since we're really dealing here with opposite and adjacent, I'm going to use tangent. So we have opposite over adjacent, which was 20. Now, I'm just going to rewrite this. I'm going to write, instead of x over 20, I'm going to write 1/20th x. They're obviously the same, but it certainly looks like it's easier to take the derivative of 1/20th x. Okay. Now again, if 20 had not been set, if that had been a changing quantity, for example, I'm moving the searchlight back, or I'm moving the searchlight forward, or something like that, at this point when I do the derivative, I'd have x over y, I'd have to do quotient rule. Okay, but in this case it is constant. So the derivative of tangent is secant squared, so secant squared theta d theta dt equals, the derivative of 1/20th x is 1/20th dx dt. Okay. Substitute and solve. Now the right side of this is very easy, of course. It's just going to be 1/20th multiplied by 4. Unfortunately, the other side is not as easy. But we can use what we know about trig here to get a value of secant squared theta. That's what we need to do here. We need to somehow, have a value for this so we can divide both sides and solve for d theta dt. So here's what I'm going to do. Okay, I'm going to do a little work right over here. I'm going to fill in the triangle, okay, and I can rewrite the triangle right over here if I want. This was 20. We were doing this from when the man is 15 feet away. I could use Pythagorean theorem, and I can get that this is 25. Okay, so secant squared, or secant, relates to cosine. It's the reciprocal of cosine. So cosine is equal to adjacent over hypotenuse. So in our case, cosine is 20 over 25, or 4/5. Well, if the cosine is equal to 4 divided by 5, then the secant, which is the reciprocal, is equal to 5 divided by 4. Well, I'm not interested in secant. I want secant squared. So I square both sides. I get 25/16. But now I can substitute. I know that secant is equal to 25/16. So I could substitute that in over here. So I've got 25/16 d theta dt equals, 4/20ths or 1/5. So I could, I need to divide by 25/16 or multiply both sides by 16 over 25 like that. And then I end up with d theta dt is equal to 16 over 125. And the units on this, because it's an angle, is going to be radians per second. Okay, so the hardest part about this is probably, this kind of blue box over here, but do not let that stop you. That is, that's just, we needed to know what secant squared, what numeric value that had in this particular problem. So we go to cosine. I just used the triangle using my trig that, I knew that the searchlight was 20 feet away, the man was 15 feet away, used Pythagorean theorem, and then just progress your way down. Adjacent over hypotenuse, fill in the values, secant's the reciprocal, square it, and then I just substituted. Again, what made this problem a little bit easier was the fact that the adjacent side was just 20. If it wasn't, as I said, the searchlight was moving, maybe I'm pulling the searchlight back to get a better angle at aiming it at the man, then over, right here, it would have been x over y, so my derivative would have been, low d high minus high d low across the line, square the low. So it would have been like y dx dt minus x dy dt all over y squared. I didn't have to do that here, but that's certainly a possibility of a problem in the future.